Hello, my name's Matthew Gardiner, the artist and creator of Radiobots. Here we are in the workshop in Shepparton, and it's in regional Victoria in Australia. Radiobots is a project that's about transferring movements and rhythms from a percussionist into a building. Making robots that respond directly to the percussionist's hand. The project has been designed to attach to various parts of a building and turn the architecture into a percussive instrument. The starting point for this project was a dream. And in the dream, I visualised a master percussionist performing in an architectural space, and he was making some of the most amazing sounds, tapping the architecture, and also these little radio bots were there helping him, tapping rhythms. What I want to do today is take you through the basic process of building and design of the Radiobots. This early prototype that you can see here is the very first proof of concept, where we were able to take an electronic pulse and transfer that through a motor into a percussive strike through the spring. Once we'd decided that this was going to work, we went on to a 3D design process. That 3D process allowed me to test out visual ideas as well as test out mechanical ideas at the same time. Starting with this early model, which was quite resolved and had one beater on the robot. That moved on quite quickly to something more like this, which is the finished model. The blue parts were then taken to a 3D printer. At the 3D printer, they could take exactly what I designed in the 3D software and through an output create these a part like this and like this one. And these are the master parts. Then they're moulded into silicon. And so the original part was embedded in this box. I poured the silicon over it and then let the silicon set. Then I was able to take the original part out and then mixing up the materials here in a little cup, carefully measured, adding a little bit of blue dye in there. I would then pour the material into the mould, wait for a few hours until it had set, making sure it got a bit of time in the oven. Then I was able to demould, and that's what the part comes out like. It's then ready to go into the oven where it gets cooked. It's a simple $40 oven, which has been retrofitted with this temperature control system. We set the temperature on the bottom where it stays constant at 66 degrees for 5 hours. Then it's time to machine the parts. So I take a normal drill press, drill out the holes, and then using a tapping tool, cut a thread into the hole. Then it's ready to be assembled once all the parts have had that additional machining. So the parts go together like this. Part would fit into there, it would get drilled in, the screws into here, the next parts go on top, and finally the mechanics are on this side, and finally it goes together. And then screwed together, we'd put the electronics in, attach the motor, the cam, and also the spring steel, which is the engine for the percussion. Once we've got a finished and assembled robot, it's ready then to go into the electronics workshop, where it's all brain and its transmitters and electronic components will be fitted so that we can have a complete working Radiobot.
I'm Ray Garrdiner, and I'd like to talk about the design of the electronics behind Radiobots. We started off with an accelerometer to detect the hits on the pad. This is the accelerometer board, which is inside each of the touch-sensitive pads. This is the accelerometer. This is a blue LED, that's a microprocessor, and whenever the acceleration changes, the microprocessor picks up a change in the analog signal and turns the LED on and sends a signal to the transmitter, which is a separate module. The transmitter, which is a pre-packaged transmitter, we opted to use something that was already available and designed the system around it. They transmit on the ISM frequencies, Industrial Scientific Medical, which is a licence-free low power band in Australia. The transmissions are encoded so that a particular transmitter is encoded to a particular bot, so that each particular pad can then be hardwired to activate a particular radio bot. Inside the radio bot we have a receiver, which is like that, and that's the companion to the radio transmitter we just looked at. The main challenge was to design something that could be remotely located, for example, put up on top of a building and stay in operation for weeks, months, in all weathers. They're not readily accessible. You can't run power cables up to them, so we designed a system that would be battery powered, self-contained, with as many recharging options as we could fit in. We opted to go for a new battery technology called lithium poly. Incredibly high capacity, very lightweight. The most common product that you find these in is the current generation iPhones. The only problem with lithium poly is that they require a special charger, and so part of the key to this design is the tiny little chip there in the middle, which is a dedicated charger designed for lithium poly. Both the radio transmitter and the receiver we did custom circuit boards for. The receiver circuit board looks like this. We've gone for as simple a solution as we possibly can, giving maximum functionality. With this particular design we can charge off mains power, we can charge off solar power, we can charge from other batteries if need be. All we need is a 12-volt power source. One reasonably small solar panel would probably charge a half a dozen RADIOBOTs in an installation. I'll quickly step through what the processor on the receiver is doing. The first thing it does is it waits for a signal from the radio module telling it it's been activated. If after 2 seconds it hasn't received a signal from the radio receiver, it flashes the blue LED on for 15 milliseconds and goes back to waiting again. The signal from the radio receiver lasts for 100 milliseconds or so, so even if a signal arrives while it's flashing the LED, it still doesn't get missed. Assuming we do get a signal from the radio, the first thing to do is to turn the motor on, to turn the blue LED on, which gives us an indication that we've received a signal. Then it waits for the motor to rotate to the point where the spring touches the contacts. Once it sees the contact close, it then waits for it to release. So the program adaptively changes its timing according to the mechanics. Now, the only thing we have to adjust with the mechanicals is the spring tension and how high off the surface the device is striking. Once it's reloaded, then turn the LED off and go back to waiting for another signal. So that's a quick overview of how the system operates.